Yeah, thank you. Alright, so welcome back and back to the difficult case. Right, so this is the case where we are not able to yet complete the proof. But I want you all to try it. Try a similar approach and see why you get stuck and what assumption would help you in getting unstuck. Right, see if you can figure that out. Supposing you make some assumption, then can you finish the proof? What is that assumption? Figure out? Right, so the idea is to try something very similar. Oh, I see. So that was for the case when both edges are on one side. Now we are in this case. So C minus F is a tight cut of G minus R, and the C minus F contractions are G1 minus R and G2 minus F. Yeah, these are the two C minus F contractions of G minus R. Yeah, we know that B of G1 minus R is equal to B of G1 minus 1 by induction hypothesis. That is fine. And B of G minus R is equal to B of G1 minus R plus B of G2 minus F. Right? This much is fine. Yeah. G1 minus R also we know is B of G1. So I'll just subtract 1 at the end, plus B of G2 minus F minus 1. All is so far so good. What we really want is B of G minus 1. This is what we want. That's what we are trying to prove. Which is equal to B of G1 plus B of G2 minus 1. Yeah. Oh, sorry. Yeah. This is what we want, which is the same as this, but this is what we have. So the only difference is these two terms. we know by our earlier result that B of G2 minus F is at least B of G2. Right? But that won't help us. Right? At least will not help us to actually put equality here. What I want is an equality here. So, but if this were an equality, then we'll be done. You all agree? If this were an equality, we would be done. So the hypothesis in which case we are done is actually this case. If for some reason, for some magical reason, if B of G2 minus F is equal to B of G2, then we are done. This would be great. Yeah? You all agree? The problem is it may not be true. It may be strictly greater than. In general, proving that an edge is B invariant is not easy. This is what started the entire journey of Carvalho-Lucchesi-Murthy in this subject. So what we really want is we want to somehow prove that this F is somehow a B invariant edge in G2. B invariant means the B function doesn't change. Right? So if we could prove that F is B invariant in G2, then the proof would be finished. The problem is proving that an edge is B invariant is generally pretty hard. Right? Which is what part 2 of the book actually deals with. Right? So this is not easy. Right? So this is why we are stuck. We don't know whether F is B invariant in G2 or not. Maybe I should define B invariant. I'm using it a lot. So this is the same as saying, if this is equal, it's the same as saying that F is B invariant in G2. This is what we need to finish the proof. Right? How do you prove that? In fact, in general, an edge need not be B invariant in a matching choreograph. Right? So now we need to figure out how to finish the proof despite this obstacle. Right? So there may be many ways to finish it. While during the break, Manoj was mentioning possibly using peripheral tight cuts. So that is something worth trying. Can you use a peripheral tight cut to finish the proof? We don't know. What we will do is we will use special types of tight cuts. Right? Any guesses? Any guesses what we will use? ELP. We will use ELP theorem. Yeah. So we will use the ELP theorem, and instead of taking an arbitrary tight cut, we will choose ELP cuts, barrier cuts or two separation cuts. Yeah. And we will also make use of this assumption. Whenever this assumption doesn't hold, we know how to finish the proof easily. Yeah, because we are in the easy case. So we'll make use of all these things to finish off the proof. Yeah. Okay, let's do it. So, yeah, I think you all have the picture in mind, right? This is what it looks like. And I've already written down the main assumption. So let me get rid of this general picture. Now we'll draw ELP figures. So either the graph is not bicritical, or it is bicritical but not 3 connected. That's one way to think about it. If it is not bicritical, then there is a non-trivial barrier, if and only if, right? So by ELP theorem, either G has a non-trivial barrier, I can make it slightly stronger, or this does not hold, which means G is bicritical, and G has a 2 separation cut, and G has a 2 separation. I'll just say 2 separation. Do you all agree? Either graph is not bicritical, which is the same as saying it has a non-trivial barrier, or it is bicritical, in which case it must have a 2 separation. Because bricks are precisely the 3 connected bicritical graphs. That's equivalent to ELP theorem. Right? So this is one way to think about this. So let's consider the case 1. Yeah. G has a non-trivial barrier. Yeah. So let's draw a non-trivial barrier. This is my barrier B, and I have a bunch of odd components. What can we say based on this assumption? See if you can figure it out. I'll comment out to you. Based on star, what can you deduce? Can you get more information in this figure? It's similar to some of the things you have done in chapter 8. In fact, I'm almost thinking that maybe one should prove this result along with the minimal class containing even 2 cut result. But maybe that becomes too much. So maybe that is why we should repeat the arguments. So the general observation that I think almost everybody has reached is that you can't have too many non-trivial components. What is not clear is what is too many. Some of you are saying there is at most one non-trivial component. Some of you are making a weaker claim that there are at most two non-trivial components. Right. So one of those claims is definitely correct. So therefore there are at most two non-trivial components. Can we go from at most two to at most one? That is what I would like you to think now. How do you do that? If you can, right? So at most two is clear. If you have three non-trivial components, well, the point is the cut has to intersect with each of them in one. And these are disjoint cuts, right? This is clearly disjoint from this disjoint from this. I mean, the set of edges is disjoint, right? So one of E and F can be here, one of E and F can be here, and now there is nothing else left. So it is clear that there are at most two non-trivial components. That part is clear. By star, G minus B has at most two non-trivial components. And since the graph itself is non-bipartite to begin with, it is at least one non-trivial component. So there are only two possibilities. Has one or two non-trivial components. We want to get to one actually. And in fact, I had kind of forgotten this detail. I thought we could directly get to one, which is why when some of you told me we can get to one, I was like, yeah, sure we can. But it looks like the case of two non-trivial components needs at least some consideration. It is not immediately ruled out. So if this is the case, supposing there are exactly two non-trivial components, then we know that one of E and F has to be here and the other one has to be here. Now we need to arrive at a contradiction if we want to conclude that there is at most one non-trivial component, right? So, but immediately it's not clear. Immediately by using star, it's not clear why this situation is forbidden. Star itself doesn't prohibit this. Yeah, you all agree? Am I missing something? All good? Yeah. So maybe we have to use something else to arrive at a contradiction in this case. So maybe that is something you all can think about now. How do you arrive at a contradiction in this case? So if you are stuck in this case, think about the core. Whenever you see a barrier, you should think B for barrier, B for bipartite. Right? So think about the core and see if you can use some facts about bipartite matching chord graphs to arrive at a contradiction. Okay, so there may be many ways to finish it, but probably the easiest way to finish it is to just look at the core and observe. Remember that the dependence relation, if you shrink the shore of a tight cut, the dependence relation is just the restriction of the original dependence relation to the edges you have left, right? So that means if you shrink both of these into single vertices, go to the core, E and F are mutually dependent in the core. But the core is a bipartite matching chord graph. In a bipartite matching chord graph, mutual dependence is very well characterized. Two edges are mutually dependent if and only if they comprise an even two cut. Yeah. So that means that E and F is E comma F is an even two cut in the core. Well, cuts are preserved, right? So if they form a two cut in the core or an even two cut, they form an even two cut in the original graph. But that is a contradiction because EF was a removable doubleton in the original graph. So G minus E minus F is supposed to be connected as part of the definition of removable doubleton. Right? So that's the issue, right? So therefore we get rid of this situation using the core. In the case of two non-trivial components, use core to argue that EF is an even two cut. You don't really need even, but anyways, I like even two cuts in G, and that is a contradiction. Okay, so we are done with this case, and therefore the correct situation that is remaining to deal with is this situation, also known as the special barrier situation. Special barrier is one that has only one non-trivial component. Not a big fan of special word, the term, but I also don't have a better word for it, so I suppose that is why Lucchesi Murthy keep using special. Okay, so we have only one non-trivial component, and in fact there is a stronger thing we could have done here. If F is here, then again the same argument applies. So actually F should be here. Yeah. So let me call this component K. The only non-trivial component is K. If F is not in, if both E and F are not in the edge set of K, same contradiction as before using the core. Yes, actually that is what Santosh was saying, that you can directly argue that both of them cannot be in the core. Yeah, that is a good point. That would be faster to do. Both cannot be in the core, otherwise you get this contradiction, and therefore at most one is in the core and the other one has to be here. Yeah, same contradiction. So this is the situation. Yeah. So now let's go back to our conundrum earlier. Right. So earlier we had a situation where we took an arbitrary non-trivial tight cut. We had G1 and G2. Right. And is my notation the same? No, my notation is different. G2 becomes G2 minus F. Let me change it. Yeah, let me use consistent notation. So I will make E as this edge. E is this edge. F is this edge. So G1 minus R is delete the two edges, E and F. Right. This is my cut. And I'm going to use the same notation. This is my cut C. Yeah. And G1 is basically the graph G when I shrink the complement of K. Right, and G2 is the other graph, you get the point. So G1 will actually give me this side, and G2 will be the core actually. Yeah, G2 is exactly the core. Yeah. Now do you see how to finish the proof? Yeah. The issue was this, right? This was the issue. The greater than equal to was the issue. We wanted equality. We were hoping to get equality here. But now G2 is bipartite. Yeah? So, well, bipartite graphs are nice. Yeah, everybody sees it? Now, because G2 is bipartite, B of G2 minus F is equal to B of G2. The proof is done by our earlier argument. Yeah. Since G2 is bipartite, B of G2 minus F is equal to B of G2, which is equal to 0, and then the whole proof goes through. Yeah. Questions, concerns, everybody's happy with this so far? So we are done in the case where the graph has a non-trivial barrier. Therefore, we may now assume that the graph is free of non-trivial barriers, which basically means that the graph is bicritical. However, it has a non-trivial tight cut, so therefore it has a two separation. Yeah, that's the case we are left with. Okay. Questions, concerns? All good? So now let's make a drawing for the two separation case. But we will now also assume that the graph is not the graph is indeed bicritical. Okay, this is a fact we will also use now. So, case 2. The graph G is bicritical and has a two separation. Right? Let's consider any two separation S UV. Yeah. So this is my U, this is my V, and after deleting U and V, there could be a bunch of even components. We shall not worry about the number of components. We shall simply draw two boxes. Some even components are here, some are there. One can probably conclude, I think, that there is only two even components using the star assumption, but I'm not going to worry about that. Let's see if we need it. This is the situation, right? So let me just call this, I don't know, K and L. These are some number of even components, right? Okay. So now let's try to figure out where are the edges E and F based on star. Based on star, where are E and F? Okay, think about it and I'll come and talk to you. Remember, there are at least two non-trivial tight cuts staring at us, not just one. That's a nice thing about two separations. Two separations give rise to a pair of two separation cuts. And in fact, depending on the number of components, multiple such pairs. Yeah, one point I want to mention, we do not know whether these two are adjacent or non-adjacent. So do not make any assumptions about that. Yeah, so it looks like pretty much everyone has arrived at the following two possibilities. One is up to relabeling, E and F both go to the left side. And the other possibility is that maybe E or F looks like this, but now F cannot be adjacent with this, so therefore F has to be either completely contained here or there. So without loss of generality, I may make it like this. So these are the two cases that you all have arrived at. Let's try to get rid of this case. Yeah. Use the fact that, see if you can use the fact that G is bicritical to arrive at additional conclusions and then get rid of the UV edge being one of E and F. In particular, what can you say about the number of neighbors of U or of V inside K and L? Right? All neighbors of U either is V, the vertex V, or they are in K and L. Can you make some conclusions about the number of neighbors in K and L for each of U and V, based on the fact that the graph is bicritical. In general, if I have any component, think of this as a component J. What is clear is that you must have at least one neighbor here and we must have at least one neighbor here. This much is clear. Right? This is for any component. K and L need not be components. Yeah. But for any component, you know that U has at least one neighbor in that component J, V has at least one neighbor. Can you make it stronger? Given that the graph is bicritical. This question is actually independent of the two cases, by the way. This question, U has how many neighbors in K and how many in L, that is not actually dependent on the two cases that I have drawn. That is a more general question I'm asking. right? So what I would like you to, we know that U has at least one neighbor in any component. Therefore, in that drawing, at least one neighbor in K, one in L. But let's just look at this figure, right? Supposing this is a component. Supposing you have only one neighbor here, W. Then do you see a contradiction? We know the graph is bicritical, right? So, can you see a non-trivial barrier? It may be just slightly non-trivial, that's okay. Yeah, thank you. Okay, so observe that if U has only one neighbor in some component J, let's say the neighbor is W, observe that W and V, they comprise a non-trivial barrier. That's a contradiction, right? So therefore, in general for a bicritical graph, if you have a two separation, then we have observed that for the two separation, each vertex will have at least two neighbors in each component, right? So therefore, if we go back to this drawing or these two drawings, we know that U has at least two neighbors, V has at least two neighbors here. By the same argument, U has at least two neighbors here and V has at least two neighbors here, right? One of these edges is E, one of these edges is F. I will maybe draw E and F in a separate color. Yeah, we can do the same thing here. Here E and F are these two yellow colored edges. U has at least two neighbors here. V has at least two neighbors here. U has at least two here. And V has at least two here. These are the two drawings we have. Yeah? Yeah, all good? Now there are multiple ways to complete the proof from here. In recent months, I've become a fan of marked as components. So I will do it using marked as components. Observe that S is UV. S is the set UV. Observe that the marked as components are almost isomorphic to the tight cut contractions with respect to either tight cut you like. By almost I mean the only difference. So in fact, one way to imagine the tight cut contractions, maybe I'll draw one of the tight cuts. Let's just draw this here and this here. So doing tight cut contraction requires me to shrink this whole thing into a single vertex. So what I will do is I will think of this whole thing shrinking into a single vertex, and that vertex is this vertex. Is that okay? I will shrink all of this and make it the vertex V. Same here. I will shrink all of this and make it the vertex V. Observe that this is actually the same as the marked as component. The only difference is, in fact, all the adjacencies are actually the same. By adjacencies, I mean not caring about multiplicities. Convince yourself that the adjacencies are exactly the same. And in fact, in most places, the multiplicities are also the same. The multiplicity changes only in one pair. There's only one pair for which the multiplicities may not agree between the marked as components and the tight cut contractions. For any other pair, the number of edges is going to be the same in the two graphs. Think about that. Right? So where does the multiplicity not agree necessarily? Maybe you can try to figure that out. Right, so I suppose you all can see that adjacencies are the same, and in fact multiplicities are also the same, except for U and V. Here I am thinking of V as becoming the contraction vertex. I am not using a different label for it. Okay, so when I do the contraction, I am thinking of V as the label of the new vertex, and of course in the marked as component, U and V are the labels of the vertices anyways. Right? So the only place where the difference is the U comma V pair. Adjacency is there, multiplicity may not agree. And in fact, as you observed, multiplicity is typically going to be greater in the case of tight cut contraction. In this case, because we have at least two neighbors, it will indeed be greater. Good. Okay. That immediately means that this edge E is actually removable. There are several ways to see that E is removable actually. In fact, there may be a direct way to see that E is removable is probably even easier. Now that I think about it, I think I don't even need to use marked as components. Forget marked as components, just think about this situation. Convince yourself that E is always removable in this drawing. In a two separation, when the two vertices are adjacent, that edge is always removable.
You mean in any two separation?
Yeah, in any two
Not just
separation.
two edges.
Yeah, in any two separation. Yeah. In any two separation, if the two vertices are adjacent, then the edge joining them is always removable. counterexample. Yeah. So maybe I'll make a DIY out of this. Small DIY. G is a matching code graph. S is a 2 separation. So it is a 2 vertex cut, that is not a barrier. If S is not stable, then each edge in the graph induced by S, very complicated way of saying something, but it works, is removable. Sorry?
You can remove if
Oh, I don't need that. I don't need the assumption S is not stable. If S is stable, that set is empty. Good, thank you. Yeah. Yeah. Okay, so that is one thing you can do. In this particular case, what you can do is you can just observe that in both the contractions, E is a parallel edge. There are faster ways to do this in this drawing. Observe that in both contractions, E is a parallel edge. Therefore, if I splice the two graphs without E, I will get a matching covered graph. Therefore, G minus E is matching covered. Therefore, E is removable. Right? So that is one way to finish it here. But this is a more general thing you can use whenever you arrive at this situation in life. Right? So basically, E is removable. Contradiction. Yeah. Now let's go to this case. In this case, we are generally considering G1 to have both the edges. Is that right? G1 has both edges, so this is going to be my G1 side of life, and this is going to be the G2 side. Yeah? G1 is generally friendly to us, right? G1 is not a problem. The problem is G2. G2 is the one that creates issues. Observe that in G2, F is a parallel edge, is a multiple edge. Yeah? In G2, F is a multiple edge. Therefore, it is B invariant. Multiple edges are friendly. They are always B invariant. Right? The problem is when the multiplicity is 1. That's when the B invariance actually becomes difficult. So we are done. In this case, in G2, F is a multiple edge. This implies that number of bricks in G2 minus F is equal to number of bricks in G2. Well, this was the good news we wanted anyways in life, right? Here also we had the same thing. We concluded that in a bipartite graph, we are done. And this is so we are done in all cases. Right? So the moral of the story is, when arbitrary non-trivial type cuts don't work, go to ELP. They have figured it out. Right? Yeah. So this is how we prove monotonicity of B with respect to deletion of removable doubletons. I did not complete B plus P DIY. I think at this point it should be fairly straightforward to complete the same argument for B plus P. So we did it for the edge case. Maybe you all can try to do this now. B plus P of G minus R is equal to B plus P of G minus 1. So the same behavior that is going for B also goes to for B plus P. Basically, you just want to check that all the arguments we did here, if all the arguments here work out, right, we use this fact which we already know for B plus P also holds. So basically everything should just go through. The only case where you have to be careful is the base case, that you have to check carefully what happens for bricks and what happens for the Peterson brick. And typically it will just go through, but you should check everything. The induction step should go through even more easily in some sense, although the induction step is longer, so you have to check everything carefully. While I was doing all of these things, I was thinking about these things yesterday and last night and all. It occurred to me as a purely theoretical curiosity, which has no applications to the best of my knowledge thus far. Why just B plus P? Why not B plus F, where F is my favorite brick, which generally happens to be Peterson. But what if I just consider B plus F, where F is my favorite brick? I don't know. Then does everything go through, or does something fail because I'm considering an arbitrary brick? And of course, it's just a purely theoretical curiosity at this point. The whole interesting thing would be, is it actually applicable in any context? Are there situations where instead of the Peterson brick, some other brick plays a special role? And then does this quantity actually become relevant? Right? The whole reason for B plus P showing up in these results is not because they love the Peterson graph. I mean, they do, but it's also because there are specific results where B plus P and P both show up in formulas. So that is why you need all of these things, right? But at this point, it seems a bit useless unless you have seen results where we use these things, right? So that is why I'm focusing on B, and I'm leaving the B plus P as an exercise for all of you. Yeah. But anyways, that's all from my side for today. The plan for tomorrow is to try our best to complete chapter 9, which basically means one more result to go. We want to show that every brick, we know that every brick has removable classes. In fact, delta, at least delta, max degree, so at least 3 therefore. Every brick has at least 3 removable classes. What we would like to prove is that there's at least one removable edge, right? So what happens if you have all of them as removable doubletons? In particular, we will prove, in fact, when we get this bound at least 3 or at least delta, we actually get mutually exclusive, pairwise mutually exclusive removable classes, right? So what we will prove is that if there are 3 pairwise mutually exclusive removable doubletons, then the graph has to be K4 or prism. And as a corollary, we will get that every other brick has at least one removable edge, right? So that is the plan for tomorrow. We will see if it finishes in 2 hours, otherwise we'll continue on Monday. But I'm hoping to finish chapter 9 tomorrow and hoping to make some progress on chapter 10 in the coming week, because in the coming week we have only 2 lectures, and then we have a long break until 4th of May, when we will have a lecture by Santosh and Amit presenting exponentially many perfect matchings in cubic graphs, right? And I'm hoping to do some more lectures in the summer and finish off the entire part 1 of the book, because it's kind of sad if we don't finish part 1, if you don't see the year decomposition theory, right? So we will try to finish that in some extra lectures. Okay, that's all for today. Thank you very much.